In this video, I'll be working out the section 6.4 day 2 notes. We are still going to talk a little bit more about radical expressions or expressions that involve roots. Specifically, instead of breaking down just numbers underneath different types of roots, we're also going to see what happens when we have variables underneath roots. And it's important to note that all of the expressions that we're looking at today are monomials. So it's a little bit different if there are binomials or trinomials underneath these roots. But if you want to break down a monomial underneath a square root, cube root, fourth root, you can use what we're about to talk about in this video. So for problem number 1, I have the square root of x to the 6th, y to the 9th. And when you break down a variable, there's a quick rule that you can use to simplify this. But I'm going to suggest, since it's not listed, put a little 2 right here to remind yourself that square root implies that there's an index of 2 on this root. So just to kind of let you know, and I don't want to write this necessarily on your notes, so I'll use a post-it note, but if you remember, the square root of x squared is x, so if I kind of continue that pattern, the square root of x to the 4th would be x squared, so then the square root of x to the 6th would be x to the 3rd. And there's a really quick way that you can divide these out. If you put that little index of 2 here, 2 goes into 2 once, so that's the new power. 2 goes into 4 twice, so that's the new power. 2 goes into 6 3 times, so that's the new power. So if I were to take the square root of x to the 126 power, right, I just take 2 and divide it into that, which would be 63, so x to the 63rd. So basically, you have a different rule. You don't have to use perfect powers to break down a variable. You're using kind of a rule of exponents here. So the problem is, what happens like if I give you an odd power? Because 2 does go into 9, but it does leave a remainder. So I'll show you what to do about that here in a second. So for problem number 1, I have the square root of x to the 6th. 2 goes into 6 3 times, so that is x to the 3rd. But now the y has power of 9. So here's a quick way to think about it, and then I'll kind of show you some work. But 2 goes into 9 4 times, so there's the new power, but there's a remainder, and that remainder is going to go back underneath the root. So here's kind of the work that justifies this answer. So this is just kind of a quick explanation. If I split up the 9 on that y as an 8 and a 1, we can take the square root of this, right? So 2 goes into 8 4 times, which is this part, but then that part is way too small. The y to the 1st is too small, so I just kind of leave it underneath. So this is just kind of a side note to how we're getting that answer, but you don't have to show that work. So we're just dividing the index into the power. If there's anything left over in terms of a remainder, it will stay underneath the root. So if I look at problem number 2, not only do I have some variables, now I have an actual number that we saw from the previous video. So 50 is 25 times 2. Then I have x to the 1st, and then I have y to the 10th. So I'm going to try to break down each of those terms. We know that the square root of 25 is 5. I can't break down 2, and I can't break down x to the 1st. But I can take the index of 2 and put it into this 10. 2 goes into 10 5 times, so this is y to the 5th, square root of 2x. And so I guess I could box the answer over here as well. So we're going to practice this just some more today. I've got 9 of these problems that we're going to go over. For problem number 3, I have a negative 3x out front, and then I have to break down what's underneath the root. So 18 underneath the square root would be 9 times 2. If you want to leave it as x to the 5th and do the remainder, kind of do some mental math for that, you're more than welcome to do it. If you want to rewrite it, and I'll probably just do it one more time here, If you want to rewrite it like this, you definitely can. So this would be x to the fourth, and then x to the first, and then y to the sixth, y to the first. So I can take the square root of 9. I can take the square root of x to the fourth, and I can take the square root of y to the sixth, and then underneath I will have a 2, an x, and a y. So then my final answer, I'm going to multiply these terms out front. Negative 3 times 3 is negative 9. X to the first times x squared is x to the third. Y to the third stays square root of 2xy. So from here on out, I am not really going to split up the variables into different parts. I'm going to use some mental math to do that. And the reason why I'm not going to do it every time, just you don't need to. It's just extra work. But you're more than welcome to do it if it helps you work out these problems. So for number 4, I have a term out front, a to the fourth b squared, and then I have the cube root of the following. Now, 27 is a perfect third power. The cube root of 27 is 3, so that 3 is going to come outside. Now, the index 3 goes into 7 twice. Okay, so once again, you can kind of think about it like this if you want to. So 3 goes into 7 twice with 1 left over, but 3 doesn't go into that power of 2. So what's left underneath the cube root is an a and a b squared. So my answer would be 3, and then a to the 6, you add those together, b squared, cube root, ab squared. All right, let's go through some more here. The more you practice, the easier it is to work these out. Number 5, I have 5a to the fourth out front. I have to break down 16 underneath the cube root, so that would be 8 times 2, and then I've got an a to the 13th. So I'll keep the 5a to the fourth. Now I'll start breaking these down. The cube root of 8 is 2, so that 2 comes out. Now the other 2 right here has to stay underneath. I'll come back to that. 3 goes into 13 4 times with 1 left over. So then the 2 and then the a to the first, that's the one that's left over, stay underneath. So I get 10a to the 8th times the cube root of 2a. Number 6, I have cd to the 5th times the fourth root of 16. Fourth root of 16 is a 2, and 4 goes into 16 4 times with none left over. So this is a good reminder that maybe everything will break down and there's nothing left over, but this is another good reminder that the coefficient of 16 is treated differently than the power on C. So you have to break down 16 using the perfect power lists from the previous video, but the variable you just divide by the index, and if there's anything left over, it stays underneath. So this will be 2c to the 5th, 1 plus 4, and then d to the 5th. So then for problem number 7, we have 2d to the 6 times, now 81 is a perfect fourth power. The fourth root of 81, I believe, is 3. Okay. 4 goes into 9 twice, so that's c squared with 1 left over. The d to the first has to stay where it's at. So this is the fourth root of cd, and then put it together, this would be 6 c squared d to the 6 times the fourth root of cd. Number 8, I have negative 3 cd out front. Now I'll have to break down the fourth root of 32, that's 16 times 2, and then I have c to the 10th. I really like this problem because the breaking down the c to the 10th. So let me go ahead and get to that. So the fourth root of 16 is 2. 4 goes into 10 twice with 2 left over. Okay, so be very careful on that. 2 left over, so that's c squared. And so this would be negative 6 c to the third d. leave a little bit of space here, and then 4th root of 2c squared. And I leave a little bit of space so that way that index of 4 doesn't look like a power on D. Or you can just put a 1 here, and that would be clear as well. So just to kind of wrap things up, this is just a quick summary. Whatever this index is, you divide it into the power. Another way to think about it is take the power and divide it by the index. And hopefully nothing is left over. That answer is your new power on whatever is underneath the radical. And if there's something left over, then it would be back underneath the root. So let me know if you have any questions or concerns on this.